What's up guys? So in this video we'll be talking about the square and multiply algorithm, which is basically used to find the value of an integer raised to another integer but under a modulo x. So it's going to use the square and multiply algorithm, and it's very simple. It's an easy algorithm to implement, and I'm just going to show you an example so it can be easy to explain. Suppose I'm having a classic example here where y equals 17 raised to 22 under mod 21. So the initial values that we are going to set, and it's by default y is going to be equal to 1, a is going to be 17 as it corresponds to our formula, and n is going to be equal to 22, and x is going to be equal to 21, or the modulo. So what you're supposed to do is take 22, the first step, and convert it into a binary number. So this video is not about binary number conversion, so I've just written out the number in binary format. So 22 in binary is 10110. So another thing that you're supposed to do is just write the number of iteration, the bit value of 22 in binary, and then we're going to find the value of y, and then another value of a. So these values will be changing as we iterate through the program. So in the first iteration, the value of the bit is going to be 0. Just notice that we are reading the bits from the least significant bit to the most significant bit. So our first bit value is going to be 0. Then in the second iteration it's going to be 1, in the third 1, in the fourth 0, in the fifth it's going to be 1, and the initial value of y is going to be equal to 1. Since the value whenever there is a bit value of 0, then you're not supposed to make any changes to the value of y. But whenever the bit value of y is 1, you're just going to take the value of y and multiply it by the current value of a. So the value of a is going to be obtained by taking the present value of a squared, a times a, under mod x. And also the values of y should also be evaluated to the particular mod x, and in this case it's going to be mod 21. So in the first iteration, the initial value of y is 1, and then the value of a is going to be 16. If you take 17 squared modulo 21, the value is going to be 16. In the second value, in the second iteration, the bit value is going to be 1, and then the value of y is going to be equal to 16, because since there is a value of 1 here, then we'll be taking the value of y and multiply it to the previous value of a, which is 16. So we take y times 16, and then under mod x we get the same value, 16, and then the new value of a is going to be equal to the previous value of a squared under modulo x. If we take 16 squared mod x, the resulting mod 21, then the resulting value of a is going to be equal to 4. And in the third iteration, the value of y is going to be equal to the present value of y, which is 16, times the previous value of a, which is a, multiplied together, and then under modulo x. So if you take 64 mod x, you're going to find the value of y is 1. And then the new value of a here is going to be 4 times 4 under mod x, which is 16. And then the coming value of y is not going to change since the bit value is 0. So the value of y, which is 1, will be maintained. And then in the new value of a, it doesn't matter what bit value you're having, the value of a is always squared under mod x. So we take 16 squared and then mod 21. So if you take 16 squared mod 21, you get the value of 4. And then the last bit value, which is in the fifth iteration, the bit value is 1, and then the value of y is going to be the present since the bit value is 1, we're going to take the present value of y, the previous value of y, which is 1, and then multiply it by the previous value of a, which is 4. So the present value of y is going to be 1 times 4, which is 4. Since we are in the last iteration, there is no need of finding the a squared mod x, since it's no longer in use. So that's just the simple explanation of this algorithm in a table format. So let's see what the C++ code looks like. So it's a C++ program to implement the square and multiply algorithm. The first thing, we're going to include the normal input-output standard string, but there's an alteration here. I'm going to include the decimal to binary.hyper. This is my very own custom header file that I've created, but I won't going to be showing it here since it's not part of the video. It's just basically a function that converts a decimal number to a binary number, and it returns an array of the integer digits that are in binary format. So when the program starts, it's just going to say program to calculate m raised to n under mod x, and then it's going to have some few variables, which is power, a, and mod. So with respect to our example, m is a, and then n is going to be the power, and then x is going to be the mod. So it prompts the user to enter the value of m, n, and x, and then it creates another variable, which is a pointer. That's a very important thing to note. It's a pointer that is pointing to a decimal to binary function converter, which is going to convert the power. Since we saw here that the value that needs to be converted is the value of a, which is the power, a raised to n, 22, and in our case we also need to convert the particular power into binary. So what is going to be returned here by this function is a pointer of an array, which is a list of which contains integer which contains binary digits 0 and 1 that compose this value 22, or any other value that is going to be entered as power. And then, and under the current circumstances, I've created that the program is only going to be able to handle digits that are 20 binary digits, and not more than that, but it can be easily altered by increasing the value of the integer size here. So this is also the size of this is also the number of binary digits that will be outputted, and each binary digit is going to be of 20. Each binary number is going to be of 20 digits. And then we have the value I, which is going to be the array controlling variable. We have the value of y, which is initially set to 1, and then we have the value of base, and basically this base is just equal to a. But since I'm going to output the initial value of a, which may be altered in the current process, I need to have another value that is going to be maintained, so that when I output at the end, the value that the user entered may still remain the same. So since we are iterating, we'll be iterating as long as I is less than the size, which is 20, so that we can read all the returned values that are integer values. Suppose we have an integer, say 10. Suppose we have a binary which is 10110, and there follows other many and useless zeros at the beginning. Since they're the most significant bits, then they will be having there are 1, 2, 3, 4, 5, and 6. There are five binary digits, and preceding these digits there will be other 15 zeros just to make up 20 binary digits. And so we are going to be looping in each and every single digit, and the thing that we'll be doing is that we'll be checking if the binary digit is 1, and if the value is 1, then we'll be multiplying it, then we'll be squaring it and multiplying the previous value of base, or the previous value of a to y, and then we do mod the modulator. And so we're checking if the current binary digit is 1. If it's 1, then the value of y is going to be equal to y times the previous value of base, and base is simply equal to a, which is currently 17, the value that we are going to be using as for demonstration. And then it's going to be doing the modulus operator using the mod, which is also another value that the user enters. And since we do not care whether the binary digit at current time is 1 or 0, we're just going to take the base squared, or the value of a squared, under mod, and then we'll be incrementing. Since this is an array, this is an array incrementation operation, we'll be moving to the next array, and the value of I is also going to be increased. And in the end, we'll be display the output as a raised to power mod the particular modulator, equivalent to the resulting. So suppose we are having an example. Let's perform the classical example that we are having, which is, yeah, it's taking some time to compile, but let's hope it works. And then, yeah, program to calculate m raised to n under mod x. So we have m, which is 17, and then we have n, which is 22, and then we have x, which is 21. So 17 raised to 22 mod 21 is equivalent to 4. That was a very quick way of explaining this program, but I hope you guys understand. Just let's perform another example where we have any value 34 raised to 12 and mod 34. So the value is 0, and I particularly believe the algorithm to be very correct. So just that's how we implement the square and multiply algorithm in C++. Thank you for watching.